Right, so we have to discuss question number 8, 9, and 10. So I have shared the screen for 8, 9, and 10. So we will quickly go through these questions without taking much time. As usual, question number 8 and 9, 10 are basically from inorganic, industrial, and environmental, and finally some small part from the electrochemistry. So question number 8, again, it is based on the first part is A. Part A is based on the analysis, cation and analysis. So we will go through it. Okay. An aqueous solution of P contains 2 cations and 2 anions. So remember, there are 2 cations and 2 anions. The following experiments were carried out to identify these cations and anions. P was acidified with dilute HCl and H2S was bubbled through the solution. So a clear solution was obtained. So the first thing is when it is acidified with dilute HCl, so basically there can be some as you know, in group 1 there should be like Ag plus that can be precipitated, as well as Pb2 plus and Ag22 plus. So what this means, these precipitates can be there. So it is Ag22 plus, mercurous. And then when you supply H2S to the filtrate, you know, there are some precipitates, about 9 precipitates that can be formed. But the observation tells that a clear solution was obtained. So which gives you the idea these sulfides or the chlorides are not formed, right? So for an example, Ag plus, Pb2 plus, Ag22 plus are not there. And after that, the rest of the sulfides in the group 2, like copper, mercuric, lead, bismuth, and then some of stannous, stannic, all those cadmium. So all those precipitates, all those anions, all those cations are not here in this solution. Then that is the first idea that you can make. And then the above solution was boiled. So first we remove H2S. So you know, if there is H2S, it can be going through some other reactions. For an example, was removed, a few drops of conc HNO3 were added. So when conc HNO3 is added, it's oxidizing agent. So sometimes if you have some amount of H2S, this can oxidize this H2S to either sulfur, and it will be like a problem for our precipitate determination. So it is not good to have H2S here. Okay. The above solution was boiled till H2S was removed. A few drops of conc HNO3 was added. So if you remember about group 3, we normally add this HNO3 to convert Fe2 plus. If Fe2 plus is here, you can convert this to Fe3 plus by adding conc HNO3. But don't forget, if Fe2 plus having enough concentration here, when you add H2S, still there is a possibility this Fe2 plus gets precipitated. Okay, but this is not compulsory. Here it gives a clear solution, because if there is Fe2 plus here in this solution as one of the cations, the concentration of Fe2 plus might not be enough to exceed the KSP of FeS here in the first observation. Okay, so that is one idea. So normally we add conc HNO3 to oxidize, and the solution was heated further. Yes, so we heat, then we add the buffer solution, and they have observed brown precipitate. So this clearly gives the idea this should be ferric hydroxide, because you know in the group 3 aluminium, chromium, and ferric hydroxides are formed. Aluminium is white in color, chromium is dirty green, and ferric is brown precipitate which was identified here. Okay, so what could be the cation that is present in the solution? So basically it should be Fe2 plus. Okay, so don't forget about that. That is one idea that you can draw from this observation. Okay, and the third, Q was removed by filtration. So ferric hydroxide was removed by filtration and H2S was bubbled throughout the filtrate. So now you know here the condition is basic, as we have discussed previously also. When you add this buffer, ammonium chloride, ammonium hydroxide, the solution become a little bit of basic in nature. So when you add H2S, now there will be other sulfides that can be formed. For an example, manganese sulfide, cobalt sulfide, nickel sulfide, zinc sulfide. So all these 4 sulfides can be formed. But what is the observation? A pale pink. So what is the pale pink color precipitate that can be formed? It is manganese, right? So here MnS is going to form. Basically, we have then Mn2 plus. R was removed by filtration and the filtration was boiled till H2S was removed. So we have to remove all the H2S again. So then ammonium carbonate was added and clear solution, which gives the idea there is no calcium, strontium, or either barium. So these are not there, 2 plus, okay? The cations are not there. But in fact, we don't need to worry about the rest of the steps because we have already found one is Fe2 plus, the other one is Mn2 plus, okay? But we have to go through the other steps as well to check whether if you have some other details that can be taken, okay? A dilute NaOH was added to a fresh portion of P. So fresh portion of P means P contains surely Mn2 plus and Fe2 plus. A dirty green precipitate and a white precipitate were formed. So you know that when you add NaOH to Fe2 plus, it converts to a Fe ferrous hydroxide, which is like a dirty green color in color, dirty green in color, and Mn2 plus when you add this NaOH, so manganese hydroxide is formed, which is white precipitate. Okay. So it is very nice. So we have identified the 2 cations from the observations given here. And then they have done some tests for the precipitate. So basically here it is ferric hydroxide, the precipitate. And here is MnS, right? So Q was dissolved in dilute HNO3, okay. And salicylic acid solution was added. So what is actually happening here? Q is ferric hydroxide, which contains Fe3 plus. So one of the identification reactions of Fe3 plus is the addition of salicylic acid, which gives you a purple color. So this confirms whether this is Fe2 plus or Fe3 plus. So this is Fe3 plus, okay. R was dissolved in a dilute acid and dilute NaOH was added to the solution. So basically R means now MnS, a white precipitate is formed and it turned brown on heating. So you know why this is turning brown. That is due to formation of MnO2, right? So don't forget about that. Because in the basic medium, when you have diluted NaOH, this white precipitate, which is formed here after the addition of little bit of NaOH, which is manganese hydroxide, is converted to manganese dioxide. So these are the observations and the specific tests for Q and R. So we have found the cations, 2 cations. Now it's time to move to the anions, right? So barium chloride solution was added to P, a white precipitate. So if you remember, we have already discussed about the addition of barium chloride in many cases. So when you add, so basically it can be either barium sulfite or barium sulfate, right? The white precipitate could be barium sulfite or barium sulfate in many cases, right? The white precipitate was separated by filtration and HCl was added. The white precipitate was not dissolved. So you know if it is barium sulfide, when you add H plus, so it dissolves. But for barium sulfate, when you add H plus, it will not dissolve. So basically, one of our anion should be SO42 minus. It should be the sulfate, right? So we have found one anion as well. So the anion is sulfate. One of the anion is sulfate. So what could be the other anion? We will check. Chlorine water and chloroform were added to a portion of the filter rate from 8.2. So for this filter rate, after precipitating out barium sulfate, and the mixture was thoroughly shaken, a chloroform layer turned yellowish brown. So, you know, we can perform the chlorine water tests for like Cl minus, Br minus, and I minus. So basically with this one, nothing happens, but Br minus, when you can oxidize this to Br2, which gives this yellowish brown in color, and I2, this gives a purple in color. So this anion that is present here is Br minus. So which concludes our discussion of the identification of these cations and anions. So basically, what are the cations that we have? Fe2 plus, manganese 2 plus, and the anions are sulfate and Br minus. So you see here, if you know your cation and anion analysis really well, this wouldn't take much of time to get the conclusion in, okay? So identify the two cations and two anions in solution P. So they have not asked to write down the reasons, so you don't need to worry about that. Write the chemical formula of the precipitates Q and R. So Q is ferric hydroxide and R is manganese sulfide. That is done. Give reasons for the following. So removal of H2S in experiment 2 for cations. So I told you before about this. Like if you did not remove H2S here completely, this conc HNO3 can oxidize this sulfide to sulfur, which interferes our determination of the precipitate. That is one thing. The other thing is, if you did not remove this H2S here, and if the solution contains this Fe3 plus, already contains some amount of Fe3 plus, this Fe3 plus can reduce to Fe2 plus, right? While this S2 minus can oxidize to either sulfur or sulfite or sulfate, we don't know. Okay, so there is another interference, right? So you can write one of the two, that is your wish. And heating with conc HNO3 in experiment 2 for the cations. So what is the main reason for adding HNO3? The main reason is if you have Fe2 plus, you can convert that into Fe3 plus. Okay, that is the main reason. So if you want to elaborate more, you can tell that when you add NH4Cl and NH4H, you are expecting to precipitate this Fe3 plus as ferric hydroxide, which gives you the idea we add conc HNO3 because Fe2 plus concentration is not enough to be precipitated as ferrous hydroxide. So because it needs to exceed its Ksp value. Therefore, we add HNO3 so that we can convert this Fe2 plus into Fe3 plus, which has an enough concentration and its Ksp value is very small, so that the ionic product exceeds its Ksp value and precipitated out as ferric hydroxide. Okay, so you can write down those two reasons for H2S as well as the addition of HNO3. Okay, so this is also done. Right, so we have to move then to the part B. So you see, this is a very, very simple question, right? Even the questions are very, very small. You just need to go through the observation to get the cations and anions. So we have to move to the part B. So what is in there? Sample X. So sample X contains lead, Pb, copper, and some sort of inert material. So we don't know what is this inert material. It is inert. And the following procedure was carried out to analyze the lead and copper present in this X, right? So a mass of 0.285, X was dissolved in a slightly excess diluted HNO3. So basically, when you dissolve in HNO3, basically what is happening here? Copper 2 plus and Pb2 plus is formed. There is this clear solution. And NaCl solution was added to this clear solution. A white precipitate was formed. That is why. So when you add NaCl, clearly you have to understand what is happening here. PbCl2 is going to form. So this is our precipitate Y, right? And then the precipitate was separated. So this is separated and the filtrate was Z. So basically the filtrate contains copper 2 plus. So this is our Ez. So what they have done to PbCl2 is here. And what they have done to copper 2 plus is here. Right? So this entire process is just to make your timing very, very small. I have mentioned that in the board. So we will go through that very quickly, right? So the idea is clear. We have this inert material, the sample, and we have added diluted HNO3 to dissolve them. Then the precipitate and the solution is formed. So first what they have done is they have added this hot water to the precipitate Y, which is PbCl2. So you know in hot water PbCl2 dissolve. So basically Pb will be present as Pb2 plus, majority of them. So when you add K2CrO4, as mentioned in the description, they were able to see a yellow precipitate. So this should be lead chromate. And again, they have dissolved this in acidic medium, which converts this chromate to dichromate because they were able to observe the orange solution. So you know, we have seen many times also when you have a chromate and a dichromate solution, they are always in equilibrium. So this equilibrium will exist there, right? 2H plus 2 chromate giving dichromate and water, right? So there is a stoichiometric ratio between chromate to dichromate as 2:1. Okay, so 2 chromates combine to give 1 dichromate. And then they have added excess Ki. So you have to know this one. When you add excess Ki, I minus going to oxidize to I2. And then the dichromate solution is going to reduce to chromium 3 plus, right? Then the liberated I2, then it's the normal procedure. They have titrated with sodium thiosulfate, and the volume and the concentration of sodium thiosulfate is given. That is one process. And the filter rate, copper 2 plus, what they have done here. So you have the copper 2 plus solution here. So they directly add excess Ki. So the I minus is going to oxidize and copper 2 plus is going to get reduced as in these equations. So you can see the equation here. What is actually happening here is copper 2 plus get reduced to copper plus. So it is very simple. And I minus is going to oxidize to I2. So I minus is going to oxidize to I2, 2I. So you have here it is a 2 electron process, and here for copper 2 plus to copper plus you have to add 1 electron. So it is a single electron process. So you need to multiply this by 2. So that is why here the stoichiometry is 2:2 and 1:1. So basically the stoichiometry between I2 and copper 2 plus, that is the case that we are interested, is 2:1. Because this coefficient is 2, coefficient is 1. So what are the questions? So the idea is we need to find the amount of copper and lead in this mixture, which has a mass of 0.285 grams, right? So these are the details. So according to this detail, you have to understand the easier part is to first find the amount of copper in the sample because it has only one reaction. But here you have to go through many reactions that is happening. Okay, So first we will check how to calculate the mass of copper. Okay. So you have the amount of sodium thiosulfate that is consumed. That is 0.1 m 15 into 10 to the power minus 3 if you find the number of moles. From this one, you can find the amount of copper 2 plus that is present in the solution. Okay. So first thing is you find the number of moles of sodium thiosulfate, and the stoichiometry between sodium thiosulfate is to I2 is 2 is to 1. So you can write down like the amount of I2 is 0.1 into 15 into 10 to the power minus 3 divided by 2, because stoichiometry is 2 is to 1. That is one thing. The second thing is, so when you find the amount of I2 here, according to this equation, it becomes copper 2 plus is 2 times the I2 value. So you again multiply this by 2, right? So you again multiply this by 2. So what is happening there? So automatically divide by 2 multiplied by 2 is going to cancel out. Okay, but you are here now. So you are here. You know how much copper 2 plus is present in this filter rate, right? So you know the number of moles of copper 2 plus. What you have to do, just multiply by the copper weight, because 2 plus means just the removal of the electron. So when you remove electron, the mass is not changed. So you have this small amount. So this 2 and this 2 is going to cancel out. So the amount of copper 2 plus is known. So it will be 1.5 into 10 to the power minus 3 moles from this calculation. So here you know it is 1.5 into 10 to the power minus 3 mole. And to get the mass, you need to multiply it by 63.5 gram per mole, which is the mass of copper. To get the percentage, you have to divide this by the weight of the sample, that is 0.285 grams, and multiply it by 100. So that is the calculation for this one. Okay. So here it is 1.5 into 10 to the power minus 3 moles. Then you multiply it by 63.5, which is the molecular mass of copper, to get the mass of copper. Then you divide by the total weight, that is 0.285 grams. Then multiply it by 100 to get the percentage value. Okay. So you find the amount of copper present in the sample. That is done. Okay. However, to find the mass of the lead present in the sample, you cannot just subtract 0.85 minus the amount of copper present, because additionally you have the mass of this inert material. So that is why they give this inert material, right? Because if there is no inert material, the sample only contains copper and lead. So you find the copper mass, then you subtract by 0.285, so you get the mass of lead. That is very simple, right? So to avoid that one, they give some sort of inert material so that you cannot subtract directly. So we have to find this lead separately. Okay. So how to find this? It is again very similar. So here they have given the amount of sodium thiosulfate that is consumed. So here it will be 2.7 into 10 to the power minus 3 moles. If you calculate the number of moles, then how much I2? It will be half of this, 2 is to 1. And then you have to balance this equation, where your dichromate is reduced to chromium 3 plus. And here, in fact, it is not Bb2 plus is from the precipitate. The reaction is from I minus getting oxidized to I2. Okay, so this reaction is very simple. I think I don't want to explain that more, but however, I will try to explain briefly the reaction that is happening. So I minus is going to oxidize to I2. So 1 iodine to 2. So I have to balance the iodine first, then the charges. So I will put here 2 electrons. So 2 minus, 2 minus, 2 iodine, 2 iodine. Then the dichromate, Cr2O7 2 minus, 2 chromium 3 plus, because the medium is acidic. So 1 chromium, 2 chromium. So I am going to balance chromium. So chromium is done. Then 7 oxygens, therefore 7H2O, 14H plus, because there are 14 hydrogens here. Then the charges. So there is plus 6 here, plus 14, and 2 minus is plus 12. So make here plus 6, I can add 6 electrons. Okay. Then you need to balance these two. So here there are 6 electrons that is consumed here. So this one should produce 6 electrons. So I have to multiply this by 3. So here my I2 becomes 3 and here this becomes 6. Okay. So this will be the balance equation when you add these two. So what is the ratio between I2 and chromium dichromate? In fact, we have to consider about the dichromate. So this will be 3:1. So if you find the amount of iodine liberated here by using this one, then you can find the amount of dichromate using this one. So it is basically again divided by 3 because this is 3:1, right? And then come here. If you get the dichromate value, so you can find the amount of chromate, that is 1:2, which means you need again multiply this by 2, right? Then if you know the amount of chromate, this should be equal to the amount of Pb2 plus, because the stoichiometry here is 1:1. Then what you have to do, you have to just multiply it by the molecular weight of lead, again divided by the total weight, that is 0.285 earlier, which is similar as this, and then multiply it by 100. Okay, so this is very simple calculation, but don't forget you have to write down each and everything as a step, because you have to write down this equation first and calculate the number of moles of sodium thiosulfate. It is 2.7 into 10 to the power minus 3. Then you have to write, therefore, the amount of I2 is 2.7 10 to the power minus 3 divided by 2. That is the second one. Third one, what you have to do, you have to balance this equation and write the overall equation and tell the amount of dichromate that reacts with I minus to give the same amount of I2 as here, 2.7 into 10 to the power minus 3 divided by 2. Then you can tell the stoichiometry is 3:1. Therefore, you divide this by again by 3. Then if you know the dichromate value, you know the chromate value, it is multiplied by 2 times, right? So that is why I have multiplied here by 2. So you know all these values. Then to get the total mass percentage of lead, so you multiply by the molecular weight of lead to get the mass of lead. Then you divide by 0.285 to get the mass of the precipitate. Actually, the mass of lead in the sample, not the precipitate, mass of lead in the sample. Then you multiply it by 100 to get the mass percentage. Okay, so this is how you can perform the calculation. But don't forget, you have to write all the steps, because explanation becomes very simple. You see just one calculation, but when you write down in the answer script, you have to write down each step to get the complete answer. Okay, so this is how you can find the mass of copper and lead in the solution. Okay, so that is the way. And next question. So calculate the mass percentage of lead and copper in X. So you can write down and find the values. And write balanced chemical equation for where relevant. So you have to write all the equation which is relevant to this calculations, all the equation that is mentioned in the board, right? And what color change is at the end point in the titration carried out in the analysis of precipitate Y. So this is the analysis in the precipitate Y. So basically here I2 is formed, right? But when you do this calculation, so there is basically dichromate, which is orange, right? But you have to understand here, there is chromium 3 plus that is formed, which is green at the end. And also don't forget when you add this I2, so all I2 is going to consume, right? So when you have this chromium 3 plus at the end, there will be no iodine left. So there is this green color that is formed because of this dichromate. So initially, what is normally present here? So when you have this dichromate here in the final step of this is converted to chromium, and you know I minus is converted to I2, right? So when you have starch, this becomes blue in color. That is how we do the titration of this with the sodium sulfate. So initially there will be blue in color, but when all I2 is consumed in normal iodometric reaction, we say it is going to colorless, or in some cases white precipitate. But here, don't forget there is chromium 3 plus still in the solution. So my final color is green in color. Okay, so that's the idea. That is how you perform this calculation and the explanation. So that is done with question number 8.